So we're going to add another tool to our toolbox of methods for finding derivatives. And it's got a name. It's called the chain rule. And what this does is it's going to give us a method for finding the derivative of the composition of two functions, right? What is f composed with g, f of g of x, prime? Okay, so let's think, well, why do we need this, right? Where does this come up? Well, we already know, for example, how to find the derivative of sine of x, cosine of x, right? Okay, but how about if I want to find the derivative of the sine of 2x? I mean, it's a small change, right? But it completely blew us out of the water because we've got no tools for talking about this. But the chain rule says if I can kind of rethink a function as the composition of two functions, then I can use this formula. And we can do that here. If you think of h of x as being the sine of x, and I'm running short of letters here, let's say m of x equals 2x, then g of x is h of m of x. And our chain rule is going to give us a way to calculate this derivative. Okay. If all you want to know is how to use it, right, how to actually calculate derivatives using this rule, go ahead and skip to the next lecture. We're going to look at a bunch of examples there, and we're going to be using this a lot throughout the rest of the class. What I'm going to do here in the remainder of this lecture is I'm going to derive this chain rule, right? I'm going to show the proof, if you will, of this thing. So if you're not following along with the theoretical side, that's okay. Just go ahead and jump to the next lecture, and we'll get in and start doing examples. Okay, there's a little cleanup there. How are we going to do this? Well, I'm going to do this really using the definition of the derivative, right? Only I know a lot of the stuff we've done, we've really used that limit as h approaches 0 definition a lot. Well, in this case, I'm going to use the other one. I'm going to use the f of x minus f of a over x minus a definition. All right, so first let me rewrite this just a little bit, because this is a lot of times kind of easier to think of if we actually write this this way. I'm going to say f of g of x prime equals, what's this right side? F prime of g of x times g prime of x. Okay, that's what I'm trying to get to. So what I'm going to do is I'm going to start with this left-hand side. I'm going to start with this side, and I'm going to just apply the definition, right? F of g of x prime. But we're not going to do x. Let's do this at a. I'm going to do this at an individual point. This is the limit as x approaches a of f of g of x minus f of g of a over x minus a. Okay, so here's what I'm going to do. Assume for just a minute, okay, assume that for just a minute that there is a neighborhood of a inside of which g of x never actually equals g of a, right? In other words, g of x minus g of a is never equal to 0, right? If that's true, then I can do this, right? I can rewrite this way. This is the limit x approaches a, f of g of x minus f of g of a divided by g of x minus g of a. So that's why it was important to me that g of x minus g of a is never 0, right? If that's 0, I'm potentially in trouble. Times g of x minus g of a over x minus a. You confirm, just make it clear to yourself. These are the same. All I did was I put g of x minus g of a on the bottom and g of x minus g of a on the top. They cancel out and everything is fine, unless they equal 0. in which case they don't cancel out. And unfortunately, this can't happen. This isn't just a theoretical consideration. If we have something like g of x equals the sine of 1 over x, for example, when you get close to 0, this function, it oscillates up and down, and it goes faster and faster and faster as you get in close to 0. So you can pick any neighborhood of 0, and there is going to be some point in there where g of x and g of a are the same. So unfortunately, there's just this kind of weird special case that we're going to have to work our way around. Okay, and here's how we're going to do this. It's going to look a little weird, but just work with me. Okay, I'm going to define a new function. I'm going to define q of y, right? What is y? It's a function that we're putting in here. And I'm going to define this to be f of y minus f of g of a divided by y minus g of a when y is not equal to g of a. I'm talking about that y here because I really want you to see that the input to q is a function, not a number, right? So this is a function whose domain is functions. And however, if you let y be g of x, look at what happens to that thing. It becomes f of g of x minus f of g of a over g of x minus g of a. And that is just our difference quotient over here. When I refer to the difference quotient, this expression here is going to be what I'm talking about. Okay, so this is great as long as y is not equal to g of a. What am I going to do in this weird special case that is causing me all these headaches? Well, in this case, I'm going to let this be f prime of g of a. Okay, so here's what I want to do. I want to show that the difference quotient for f composed with a g, that's what I pointed out up there in the upper left-hand corner. I want to show that that is always equal to this function. Q, let me write it over here off to the side, is always equal to Q of g of x times g of x minus g of a over x minus a. Okay, if I can show this, then I'm actually okay doing that division. All right, so how can we do this? Well, look, when g of x is not equal to g of a, right? When g of x is not equal to g of a, then this is just, we're going to do two paths here, right? When g of x is not equal to g of a, then this is just f of g of x minus f of g of a divided by g of x minus g of a times g of x minus g of a over x minus a. Stuff cancels, and look at that. Yes, that is equal to the difference quotient. Okay. Now, what happens in the case when g of x equals g of a? Okay, well then I have to use this version down here, this f prime of g of a. So let me see if I can squeeze this in here. What happens when g of x equals g of a? Okay, in this case, first, notice that the difference quotient is 0, right? The difference quotient will be f of g of a. Let's see, difference quotient equals f of g of a minus f of g of a over x minus a, which is 0. Okay. What about our function? Right? What about our expression here? Well, in that case, this expression here, g of x minus g of a, they're equal. that means this bit is 0, right? This bit is f prime of g of a. It's a number. It exists, right? F is differentiable. So this is f prime of g of a times 0, which is 0, right? So this kind of slightly bizarre looking function here, right, is in fact equal for every value of x to the difference quotient. Okay, so excellent. Now, that means my limit over here is equal to the limit as x approaches a of q g of x times g of x minus g of a over x minus a. Okay, now I'm going to use my limit rules, right? I'm going to use my limit rules. I'm going to split this up. This is the limit x approaches a of q g of x times the limit as x approaches a of g of x minus g of a over x minus a. Okay, now this second part here, this part is easy. That's just the definition of g prime of a, right? Now, as for q of x, q of g of x, the left-hand limit, notice that q is defined wherever f is. And because f is differentiable at g, right, that means that at f is differentiable at g of a. We assumed that, right, that f was differentiable. That means that q must be continuous at g of a, right? Because differentiability implies continuity, right? So that means that this limit is equal to q of g of a. But go back to my definition of q, right? When this value is equal to g of a, that's this case here, then this is just f prime of g of a. And that's exactly what I wanted to show, right? That is this, this side of the equality, right? So that is my chain rule. So that's great. Now we've got this formula. I know the formula looks a little weird. It's maybe not a little intuitive how you use the formula to actually calculate derivatives, right? So that's what we're going to focus on in the next lecture, right? We're going to talk about how to actually use this to find derivatives. And you know, if that maybe got a little weird for you, that's okay. Go and watch the next lecture. Get a feel for how the chain rule actually works. Then, if you are following along or you're trying to grasp kind of the theoretical side of this, come back and watch this again, right? And I think you'll find that if there's spots that are a little vague to you, it might clear up a little after you see how this rule is actually used in practice.